Hi, and welcome back to Geology. So we are going to be starting our new unit, which is the history of the Earth. And in this unit, we are going to go through two different ways in which geologists can look at the layers of the Earth and kind of put them in a sequence of ages. And then we'll actually even go through the history of the Earth, talking about the different periods and eras and what kind of ecosystems were there. And even we're going to focus a lot in on what's happening in Kentucky and what kind of eras do we have present in the rock records around us, and what kind of ecosystems did that equate to. So do get out a sheet of paper and a pencil, and we're going to take some notes today on what is called relative age of rocks, which is just kind of an easy way to think about it, is just kind of just looking at what layers we have present and how we can identify them. So we're going to go through a couple of big terms and definitions in this series here. So once again, make sure that you get these down in your notes. They're going to be really, really helpful. So the first picture that I have right here, before we even jump into anything, this is an idea of what we've kind of been talking about. So we have our igneous intrusion here. This is our batholith, and you can see it's got a pipeline or a dike that leads up to an igneous sill right here, like those window sills that we were talking about. So this is all an igneous rock here. But as you can see behind it, if you kind of think about like these layers of blue and yellow and gray had to be there before this magma chamber could come in. So these, normally when we see lines like this, are sedimentary rocks. So we're going to go through and kind of talk about like these layers back here are probably much older than the layers right here. And we could also say that more than likely the layers at the bottom are much older than the layers at the top. And we're going to go through and talk a little bit about that. So determining relative age. So the granddaddy of geology, his name is James Hutton, and he is kind of the gentleman who went through and started to say, well, how old is the Earth? There was many different ideas and stuff prior to him, but he really started to look at the actual records of the rocks and not just kind of make estimates on like biblical perspectives and other philosophers. He actually started to kind of say, well, if we look at this here and the progression of what's happening, he was able to suggest that the Earth is about 4.6 billion years old. And he's actually pretty accurate, and we're going to kind of go through and talk about how that is. So once again, today we're going to look at the relative age of rock layers, meaning that what can we learn from what is in those layers and what's happening with the layers maybe above it or below it or in the surrounding area. So relative age, to give you just a real quick idea, is the order or the sequence known, but not the actual date of occurrence, meaning that when we are talking about just an idea, like I might say, you're a teenager. I might not say like, oh, you're 16 years old or 14 years old or whatever age you might be. I know in the relative area that you are somewhere, you're a high schooler. Or I might say, well, your brother is a toddler, or whatever it may be. Is that it's an idea. I don't know the actual date, but I know kind of a rough estimate. So that's what we're going to be talking about today, relative age. Whereas absolute age is being able to figure out the exact date of when an object was either born or created or formed or whatever it can be. So we'll split these both up and talk about them more. So with relative age, we are going to talk about kind of this umbrella approach of looking at what is occurring with the rock layers. And so there's this big fancy word right here, uniformitarianism. Uniformitarianism. That's a big mouthful to say, but what it is that it is just being able to explain geologic processes in a chronological order. So let me read you the definition. Principles that geologic processes that occur in the past can be explained by current geological processes, meaning that volcano eruptions that happen today possibly are pretty similar to maybe ones that happened 4,000 years ago or 4 million years ago or whatever it may be. Erosional process of glaciers are probably the same as it was in the Ice Age. So the past and present are somewhat the same in geologic processes, and that's what this is saying. Past and present are the same. The rate of time might be altered just a little bit. Something might have moved a little bit faster depending on different processes, but the idea is still there. So we're going to use this term quite a bit, is the law of superposition, which just means that more than likely older rocks are found at the bottom and younger rocks are found at the top. So you can see here, it's law of superposition. Sedimentary sequence will be oldest on bottom if undisturbed. So we talked about those ideas of sedimentary rocks and how they form in layers due to erosional processes, and they get compacted and cemented. This law of superposition kind of adds to it. So if we take a look at this picture here, we can see that we've got our plain flat layers, and then we have different objects in them. This one's got nothing in it. We've got little dots here, maybe like a sandstone. We've got some clumps in here, so maybe a conglomerate. And then we have, this is something we'll talk about. This is the youngest. It kind of overlaps everything else. So oldest at the bottom, so oldest, older. And then this one came through and cut across all of them. So it's the youngest, and we'll talk about this. This is an actual law. And this is once again more than likely an igneous formation. So uniformitarianism is, once again, this idea that you have sequencing of events, so deposits. So like if you were to go to the bank and give a deposit, this is kind of that same idea. So you have deposits of sedimentary rock that most of the time are usually some type of aquatic environment, because we have lots of erosional processes that can happen in that event. So let's take a look at this chain of events here, 1, 2, and 3. So we can see that we have deposition, deposits of layers. Normally when you see this brick layer, that's a limestone. Normally when you see this is a sandstone, and then this here is a shale. So we got 3 different types of deposited layers, clumped down, stacked on top of each other. This one formed first, the limestone formed first, then this one, and then this one. And then something happens, something with either plate tectonics or some other type of event, and we get this intrusion, this igneous intrusion, where we've got magma coming up and cutting across all of these different layers. And so we can say that these layers were here before this one. So these layers, our sedimentary layers, had to be older than our they're even calling this one contact metamorphism and intrusion. So this orange layer here had to be younger. And then there was more deposit on top of it. So then this one, now this layer becomes the youngest because it's now over top of this igneous sill or this intrusion right here. So it just keeps happening over and over. It's like almost like layers in a book, or pages in a book, or layers in a cake, or whatever it may be that you can kind of think of, is that we have this uniform process that just keeps occurring over and over again. So to kind of add on to what we just talked about is that those igneous intrusions are normally going to be the youngest, and so that's what this is saying here. Intrusions occur when molten rock flow into the Earth's surface. So think back when we were talking about igneous rocks, and we went through and we talked about batholiths and laccoliths, and we had dikes and sills and all the these different types of formation that are intrusive. And so these are forming in the earth layer, and so they're just coming up and out. So once again, molten rock that flows to the Earth's surface, due to the law of superposition, that means that this one's the youngest. It moved across all these other rock layers. And so we call those intrusions, meaning that they intruded. Think about it, these are all here, like you're at a party and you're having a great time, and then all of a sudden, like someone that you didn't invite shows up. They're an intruder, kind of like that. It's kind of the same idea as like, hey, these sedimentary rocks are having a great time, and then bam, an igneous intrusion comes through, and that's when the magma squeezes into this pre-existing rock. And so we call that the law of cross-cutting, which means that this igneous intrusion will cut across. So we've seen a couple of pictures here. There again is our intrusion. This is what it actually looks like in real life. So flat sedimentary, flat sedimentary, flat sedimentary, flat sedimentary, bam, we've got our intrusion. Bam, our intrusion. So this is what we call the law of cross-cutting, where igneous rocks cut across older rocks. So igneous rock is younger than the rock that it has intruded. Sometimes we can look at it as fragments too, pieces of rocks found in another rock. So this one right here was encased into something else, and that's going to help us sometimes figure out that law of superposition. Faults and folds. So we're going to talk a little bit about the idea that we can look at these just slightly different. So a fault occurs when there is a break or a crack in the rock due to a geologic process. Once again, this is going to be with our transform boundary. And so if we look at this picture here, we see our intrusion, but this line right here, that represents a fault. And you can see it's offset. That's what we call these rock layers. This layer should technically connect here. This layer should connect up here. And even you can see that, like, the brick layer should connect there. So they once were much closer together, and they were offset because that fault allowed one side, and we can think about it more than likely this side looks like it might have dropped down, or this side got pushed up. It got set off by some way or some form. And then we can also have folds. More than likely, this was sedimentary rock that got pushed into some kind of mountain building process, and we get these folds. And that's just where there's no break in the rock, but they bend due to crustal plate movement. So once again, these rock layers were more than likely flat, and they got squeezed on maybe this side, and that caused them to fold. So I'm going to stop here, and we're going to kind of work on a little activity, and then we'll come back and kind of finish up some of the other terms that go along with this. Thanks.